Hey guys, how's it going? Welcome to day 49. And um, this is not just a statement that is true. Integration does rule, but it's also what we're learning about today, integration rules. So these are some helpful rules that they are directly tested on, sometimes on the AP test, and then they are indirectly tested on in the fact that it's a time test, and using these rules will help you save some time and be more accurate in your responses. So let's take a look at how this works. The first rule is one that I'm going to set it up, and I want you to see if you can anticipate what the answer is going to be. So this is rule one. So I want you to think, what would be the integral from a to a, where a is some constant? What would be the integral from a to a of f of x dx? Now, we usually talk about this from a on the bottom to b at top. But now we're saying from a, so some number, to the same number. Well, if you think about it in several different ways, you should come up with the idea that this should equal 0. Okay. We can think about it as area under the curve, right? If we had a graph, here's my function. If I integrate from a to a, I don't have any area underneath the curve, so it should be 0. You could think about it in terms of like yesterday's video, solving a definite integral, right? If I find an antiderivative, right, I would do capital F of a minus capital F of a. Whatever I get for that, when I subtract it from itself, it's always going to be 0. Okay, so that one doesn't come up a ton, but when you see it, make sure you know it's 0, right? So for example, if I want to do the integral from 5 to 5 of this trinomial, I do not want to waste all of my time finding an antiderivative, then plugging in 5, then plugging in 5 and subtracting the 2. Right? I want to immediately know that this answer equals 0, and I'm done. Good. Rule number 2. Okay, so if I switch the numbers on my definite integral, right, I know that it's just going to give me the opposite signed answer. So, and you can think about this in terms of, right, that first integral would be capital F of b minus capital F of a. The second one would be capital F of a minus capital F of b. Since we're just subtracting in a different order, right? If you think about 2 minus 10 is negative 8, 10 minus 2 is positive 8, right? You get the same answer, but opposite signs. Here's an example. So I know the integral from 1 to 6 of f of x dx is 12. What would be the integral from 6 to 1 of f of x dx? Well, it'd be the same answer, opposite sign. So the 12 becomes negative 12. If my original integral is negative, then when I reverse the limits of integration, it would become a positive. If we have a constant times a function, when we do the antiderivative, we can just, I call it throwing it out front, throw the constant out in front of the integral. So then we can just work the integral on our own. Let me show you an example here of not using it and using it and showing that they give you the same solution. Okay, so I wanted to solve this, the integral from 0 to 3 of 8x dx. The way that we've been doing it before, we come up with an antiderivative, we bump and divide. And then we would say, okay, well, this is going to be 4 times 3 squared minus 4 times 0 squared. 3 squared is 9, 9 times 4 is 36. 36 minus 0 equals 36. Well, I could solve this integral in the same way by taking that 8 and putting it out front. I could have rewritten that original integral and have the 8 out front and just do the integral of x dx. If I do it that way, anytime you do this rule and you put the constant out front, I usually don't use it with polynomials. Okay, but anytime I put that constant out front like that, I have to keep writing it over and over and over again. So when I go to do my brackets, I gotta make sure that I still have that 8 out in front. Okay, then I bump and divide. Okay. This is gonna equal 8 times, well, it'll be half 3 squared minus half 0 squared. 3 squared is 9, right? 9 times half is 9 halves. So again, I have 8, and then I have 9 halves minus 0. And then so I have 8 times 9 halves. This becomes a 1, this becomes a 4, and I get 36. And you may say that didn't make it easier, and I would agree. I would do it the first way. But when we see a problem like this, okay, I like to rewrite this one with the 6 out front. I know my antiderivative of cosine x is sine x. So we can always just take a number, take a constant, and factor it out in front of the integral. If you're going to do that, just make sure every time you are doing another step, you're remembering to include that you factored out that 6 along the way. All right, the fourth rule is one you've seen before. We'll put it in here as well. This is the rule on splitting the integral. And if I have a function plus a function or a function minus a function, I can just split it into two separate integrals. Right, so if I had f of x plus g of x, I could just do the integral of f of x plus the integral of g of x. If it was minus, it'd be minus. So that's rule 4. We've seen it before, just splitting an integral. You can do two separate integrals if you want. Sometimes that's very helpful. Okay, we'll kind of see in the course of some examples here. We'll see why that can be helpful. Okay, fifth rule. Okay, take a look at this one. The first integral, you notice, goes from a to b. The second integral goes from b to c. Now, if we think of this one's easiest to kind of envision in terms of area under the curve. So the first region goes from some point A to some point B. The second region picks up right where the first one left off at B and goes to C. So that's right? So I call the A to B integral and the B to C integral the two parts, and I call A to C the whole. So if you think about this visually, so here's f of x. The integral from A to B would be this area, right? That ties to this function. That area plus this area, which again ties to our second part. And if I add those two parts of the areas, it should equal the area that does the whole thing from A to C. So I think of this as part plus part equals whole. Okay, part plus part equals whole. When this works, you just have to make sure that these are abutting each other like that. Let me show you what I mean by this. So if I know the integral from 1 to 5 of f of x dx is 6, and I know the integral from 5 to 8 of f of x dx is equal to 2, what integral could I then know the value of? Well, if I notice 1 to 5 and 5 to 8 are two parts of a whole, the whole then would go from all the way from 1 to 8. So the question would be, what's the integral from 1 to 8 of f of x dx? Well, So again, I would know that that would have to equal the integral from 1 to 5 of f of x dx plus the integral from 5 to 8. That's the rule. This is like a, b, b, c, a, c. So I would just have to add those two together. 6 plus 2 is 8. But sometimes they don't give you two parts and ask you for the whole. Sometimes they give you a part and the whole and ask you for the missing part. Okay, so take a look at the second example here. So look at this setup. I gave you the integral from 2 to 10 is 15, and I give you the integral from 7 to 10 is 6. Now, these are not two parts. 7 to 10 is a part of 2 to 10. So what I'm missing here is my other part. So the question they're going to ask is the integral from 2 to 7 of f of x dx. So again, when I take a look at this, I want to identify the two parts. Okay? The two parts are 2 to 7 and 7 to 10. 2 to 10 then would be the whole, right? That spans the whole region. So here's what I know. I like to write it out like this. I know the first part plus the second part plus the equal of the integral of the whole thing. And I just go through and say, okay, what's the integral from 2 to 7 of f of x dx? I don't know. That's my question mark, right? I'm just going to call it an x. Plus, what's the integral from 7 to 10 of f of x dx? Well, I know that that is 6. So x plus 6 has to equal the integral from 2 to 10 of f of x dx, which I know is 15. Solving that equation, I get x equals 9. So that means the integral from 2 to 7 of f of x dx equals 9. Okay. I have two more rules. I'm gonna save them for the next or a video in the future. I want to show you one example that kind of puts all the rules together. Okay, now, these are more like what the AP exam questions can be like. They're usually pretty tough, right? Or they look pretty tough, but once you start solving them, they're not too bad. Okay, so here's the setup. I know the integral from 1 to 8 of f of x dx is 17. The integral 1 to 3 of f of x dx is -4. And the integral from 3 to 8 of g of x, oh, I forgot my dx, equals 7. Well, here's the question. I want you to find the integral from 8 to 3 of 4f of x plus 2g of x. Okay, so when we take a look at this, the first thing that I want you to notice here is that we're going to end up using quite a few rules on here. As you get better and better working with these rules, you can kind of do a big simplification all at once. Okay, but I'm gonna look at this step by step for you. The first thing I notice is that initial integral looks wrong. I don't love the 8 to 3. I'm used to the lower number being on the bottom and the bigger number being on top. But rule number 2 that I gave you, if you look back in your notes, tells us how to fix that. Okay. Also, I have an f of x and a g of x, and I have constants in front of them. So what I'm going to do first here is I'm going to split the integrals. Then I'm going to throw the constant out front, and then I'm going to fix the orders of my limits of integration here. And then hopefully I'll be able to solve it. Maybe I will, maybe I won't. I don't know. Let's take a look. So first thing I want to do is this. Split these things. Okay. So I split them. Now I'm going to go ahead and factor out the 4 and the 2. I'm going to throw them out in front. Now I'm going to fix the order that they're in, so the lower number is on the bottom and the bigger number is on top. And when I switch the orders, all I have to do is just put an opposite sign out front. Right? So when this 8 and this 3 are going to flip-flop, I have to put a negative sign out in front of the 4. And instead of writing plus -2, I'm just going to say -2 integral 3 to 8 of g of x dx. Okay, so now I've split the integrals. I've factored out the constants. And I've reversed the order so it goes low to high from bottom to top. Okay, now I just have to figure out what I need to do here, right? Now I remember seeing 3 to 8 up in my selections here. I already know that the integral from 3 to 8 of g is 7. But if you notice, I don't have the integral from 3 to 8 of f. But I have 1 to 8 and 1 to 3. Right? If I think about it, 1 to 3 would be a part, 3 to 8 would be the other part, 1 to 8 would be the whole. So I'm just going to solve this up here really quick. If I know the integral from 1 to 3 of f plus the integral from 3 to 8 of f, I know, right, I'm not doing very good notation here, I just want to save some space. I know that has to equal the integral from 1 to 8 of f. So I know 1 to 3 is -4, right? I'm just plugging this in from up here. plus integral 3 to 8 is what I want, so I'm going to call it x has to equal the integral from 1 to 8, which is 17. So I'm just going to add 4 over, and I get x equals 21. So here's what I know, going back down to my answer here. I know the integral from 3 to 8 of f of x dx is 21. So I'm going to have negative 4 times 21 minus 2 times 7. 4 times 21 is 84, so times it, making it negative, we get negative 84 minus 14. I just want to add those up together to get negative 98. So overall, it's a pretty tough problem. It uses all of our integration rules, but you'll see problems like that probably on your AP exam. All right, that's it for today. I'll see you guys tomorrow. Bye.